Hey everyone, Dan Casper here. Think you know what time it is? Well, you probably don't know what time it is. It's moisture and humidity assessment time, I guess. Anyway, this lesson's on moisture and humidity assessment. So we're going to go over, I'm going to do some summary presentation of some of the content from this week. Focus on the difference between relative and absolute humidity. Talk about dew point. Discuss what a sling psychrometer tells you and how you can use it, and then how you interpret a psychrometric chart, and then also sort of give you some context. Why do we care about this, and also what causes condensation. Alright, so let's get this started. So some key terms. These are really important to know. Condensation, you should know this, is water vapor transformed into liquid water. Evaporation is liquid transformed to water vapor. We know this. So absolute humidity is probably a new term for you, unless you've done some of the readings this week, which hopefully you have, or sometimes called vapor pressure. So this is it's a measure of how much water vapor is in the air. So if you look all around you, you're breathing in water vapor. So take a nice breath. You're breathing in some water vapor in the air. You're always going to have some humidity in the air. Okay, that humidity is in the form of vapor. The amount of vapor in the air, okay, is the absolute humidity. So it tells you how much is there. Alright? So it's absolute humidity. Relative humidity, on the other hand, is the ratio of how much moisture is in the air compared to how much moisture the air can hold. And air at different temperature can hold different amounts of vapor. We'll go over that here in a minute. But as it gets warmer, as the air warms up, it can hold more vapor. Okay? And so if you have a certain amount of absolute humidity in the air, right, and then let's say you warm up the air, because that air can hold more moisture, then the ratio of the absolute to the maximum possible humidity drops. Okay, so the relative humidity basically tells you like how close are we to 100% saturated air. So if you think about a rainy day, or you wake up or at night when the dew is starting to form on the grass, and you can feel it. It's just almost feels like the air is saturated with water. It's really, really humid. That's 100% relative humidity. We get to that point where the air just can't hold any more water, and that's why we get dew on the ground. But the relative humidity tells you how close we are to that point where the air can't hold any more moisture. Okay, so that's your relative humidity. The dew point is the temperature at which condensation occurs, or otherwise is at 100% relative humidity when the air is fully saturated. So what I just mentioned, that the relative humidity will, as the air cools down, okay, the relative humidity goes up, because cool air holds less moisture than warm air. So if you think you have let's say you have 50% relative humidity in the afternoon, and then the temperature slowly starts to cool down, but the actual moisture in the air, the absolute humidity, stays the same. Okay? So you think like the air can hold this, let's say this much moisture, if you try to visualize it, and there's this much in there. But then when you drop the temperature, okay, the air can only hold this much moisture, and you still have this much in there, so you're kind of like more full, if you will. And so if you drop it all the way down to the point that like here's how much moisture you have, and you drop the temperature down to this point, and you're at that point the air just can't hold any more vapor, that's the dew point temperature. And so that's why it's called the dew point, because that's when the dew forms on the grass or on the car, is when especially in the summer, you get a lot of moisture in the air because it's warm air, right? So warm air can hold all that humidity, and then at night it cools down enough, you drop it to the point where the air it can't hold any more moisture. That's the dew point, where it's 100% relative humidity and it's saturated, right? And so the key here is, really key concept, is that warm air can hold more water vapor than cold air. Okay? So those terms are really important to know. So we use, there's a lot of different equipment that we can use to evaluate the relative humidity. one of the most common ones, and we actually have one right here. It's called a sling psychrometer. This is a picture of it is actually on the slide. But this thing is, you can spin it around. I don't know if you can, hopefully you can see what I'm doing. You spin this thing around. And it may be hard to see, but there's actually two thermometers on this. Okay. And this one, I'll pull it up close to the camera, see if you can see it. There's actually this little cotton, and this one has a cotton like sock on it almost. Okay, so that's a wick that gets wet. And on the other side, there's a thermometer, and there's no wick, right? And so what you do, as it says on the PowerPoint here, is you wet this one wick, and you wrap one thermometer in the wick. The other one has no wick around it. Okay, and what you do is you just spin it around. Okay, and the spinning, what that does is it causes evaporation to occur because of the the energy from the air. Okay, it causes evaporation to occur. And when you do that, the wet wick and the dry, the wet bulb and the dry bulb, so the wet wick is the wet bulb and the dry one is the dry bulb, they will end up different temperatures as long as the relative humidity is below 100%. So there'll be a discrepancy between the two. So here, let me actually show you here. Here's a different, there's all kinds of versions of this. You can see you have your handle here, and then you have your thing that you, excuse me, I'll get the laser. You have a handle here, and it spins around this, so you spin it around. Here's your wet bulb, okay, wrapped in a wick. Here's your dry bulb, not wrapped in a wick, right? So you spin that thing around, and what do? When you spin it around, it causes evaporation. And I want you to think about what is the heat transfer that occurs with evaporation. So does it pull heat from the air, or does it dump heat into the air? This harkens back to the last few lessons. Okay, so remember, to evaporate something, you have to add heat to it. So when the water evaporates off of this wet wick, what it does is it pulls heat from the air, and it pulls heat from the thermometer as well. Okay, so it pulls heat from everything around it, just like when the sweat dries on your skin, it makes your skin cool because of the evaporation. Well, the same thing happens here. And so if what it's doing is it's pulling heat from all around it, including the wet bulb thermometer itself, and so when you do that, it actually cools down around this wet bulb more. This shouldn't cool down at all unless there's water on it, the dry bulb. Okay, so you spin it around, the dry bulb stays the same temperature, and this wet bulb, because of that evaporation, it's going to pull heat from the thermometer, and it's going to cool everything around it down. And so once you do that, then you measure the difference between the two. You have the dry bulb temp minus the wet bulb temp, and that gives you something called the wet bulb depression, or the WBD, if you will. Okay, so what does this have to do with anything? As the relative humidity goes down, okay, the air is drier, which means more evaporation is going to occur. And you can almost imagine that, right? So like you have really dry air, think of like desert air. It's pretty easy to dump moisture into that air. It's so dry, you can really get moisture in there pretty easily. So in that case, if the relative humidity if it's a lower relative humidity, so you spin this psychrometer around and you're in a low relative humidity, you're going to get a lot of evaporation. Okay? If you get a lot of evaporation, you get a lot of cooling because it requires heat to evaporate. If you get a lot of cooling, right, your wet bulb temperature is lower, which means your wet bulb depression is bigger, right? So if the air is drier, you're going to get a bigger temperature drop on your wet bulb, and your wet bulb depression is going to grow. Conversely, more relative humidity, there's more moisture in the air. It's hard to dump more moisture in the air that's has already a lot of moisture in it. And so if that's the case, you're going to get less evaporation here. Less evaporation means less cooling. Less cooling means that this wet bulb depression will get smaller. Okay, and so that's what you use this for. You can use this to determine the relative humidity, and all you need are 2 thermometers, a wet wick, and something to evaporate that water from that wick. And the sort of extreme of this is if the air is 100% saturated. Okay, we're at 100% relative humidity. Then there's not going to be any evaporation because the air is saturated. Think about what the term saturated means. It can't hold any more moisture. And so if you spin that, you can spin that thing until the cows come home, and that is not going to evaporate, which means that this wet bulb is going to be just as wet, which means its evaporation hasn't occurred, which means the wet bulb temperature is not going to change, right? Which means you're going to have 0 wet bulb depression. So if you would have one of these, spin it around and around and around and around, and you're not getting any change in your wet bulb temperature, then as long as you did everything correctly, that means you have 100% relative humidity. Okay, and there's a couple of different ways you can interpret this. Here's one example just to show you, kind of demonstrate the relationship here, right? So we have our psychrometer, right? We take this thing, we spin it around, round and around. Okay, we get a nice. I don't have this thing wet right now, but so let's say we do that. Okay, and up here we have a dry bulb of 50 degrees Fahrenheit. We have a wet bulb of 43. If that's the case, what is our wet bulb depression? What's the relative humidity? So this is one way we can determine that. This is just a chart used specifically for a sling psychrometer in this climate zone. So we have a dry bulb of 50. So that's right. So that means our wet bulb of 43, so our wet bulb depression is 7, right? 50 minus 43 is 7. So that's how we use this chart. So we find 50 and we find 7, right? So 50 and 7, and where they meet is 55. So our relative humidity is 55%. Okay? So let's say we have the same dry bulb, but the wet bulb is 40. Okay? So our wet bulb depression is 10, right? So we go to the chart over here, we find 10, we have 50, same, and the relative humidity is 38%. So you can see that the relative humidity, okay, we kind of did it backwards, but we found out that as the relative humidity dropped, okay, remember the wet bulb gets bigger, the wet bulb depression, gets bigger, because lower relative humidity, I think I put it over here, lower relative humidity means more evaporation occurs, which means more cooling, which means your wet bulb is higher, right? So we have a 10 degree wet bulb here, or wet bulb depression, and a 7 degree wet bulb depression here. That's because of the relative humidity, okay? And that impacts you can see the dry bulb stays the same, but the wet bulb changes. Okay, so that's one way to use it. You can also use a psychrometric chart, which looks like this. And we will pick this up in the next video.